As a science-loving person, I must begin by revisiting the framework established in Part 1. According to NASA's Cosmology Division, before the Big Bang there was no classical space, no temporal dimension, and no physical matter. Instead, the universe existed as a quantum vacuum state, a field governed entirely by probabilistic fluctuations. These fluctuations are not particles in the classical sense, but temporary excitations of underlying quantum fields. In Part 1, we examined how one such fluctuation achieved a state of runaway amplification rather than collapsing back to zero. This deviation from equilibrium initiated the conditions necessary for cosmic inflation. Understanding this pre-inflationary quantum regime is essential because it defines the boundary where classical physics fails and quantum field theory becomes the only valid description. Before proceeding, I want to clarify the intent of this analysis. This video represents my personal attempt to interpret the early universe through the lens of quantum physics. None of the explanations presented here are derived from any specific textbook or academic curriculum. Instead, they synthesize publicly available research from NASA, CERN, and the European Space Agency. Combined with my own conceptual understanding of quantum field theory and cosmology, the early universe is an environment where empirical data is limited and theoretical models dominate. Therefore, the descriptions you will hear reflect one scientifically grounded interpretation among several competing frameworks. My goal is not to provide definitive answers, but to construct a coherent, technically accurate narrative of the universe's first instant. Rode. According to NASA's theoretical models, the universe originated in a state of extreme density and temperature, often described as a singularity. However, from a quantum physics perspective, the term singularity is a placeholder for our lack of a unified theory of quantum gravity. What we can assert is that all known energy, momentum, and field excitations were compressed into a region smaller than a proton. In this regime, classical spacetime loses meaning, and quantum fluctuations dominate. The Heisenberg uncertainty principle implies that energy and curvature varied violently at sub-Planck scales. This quantum point was not stable. Its internal energy density created conditions where space-time curvature could no longer remain static. This instability set the stage for the inflationary expansion that followed. In the first fraction of a second, the universe underwent a phase known as cosmic inflation. According to NASA's Wilkinson microwave anisotropy probe data, inflation expanded spacetime by a factor exceeding 10 to the power 26 in less than 10 to the power negative 32 seconds. Importantly, this expansion did not violate relativity, because it was space itself, not matter, that expanded faster than the speed of light. From a quantum field perspective, inflation was driven by a high-energy scalar field, often referred to as the inflaton. The inflaton's potential energy created negative pressure, which in general relativity produces repulsive gravity. This repulsive effect caused spacetime to stretch exponentially, smoothing out irregularities and setting the initial conditions for the formation of large-scale cosmic structure. Immediately after inflation began, the universe existed in a state of extreme temperature and density. According to CERN's high-energy physics research, temperatures exceeded 10 to the power 27 degree Kelvin, far beyond anything achievable in particle accelerators. At such temperatures, matter cannot exist in any stable form. Instead, the universe was dominated by quantum fields in highly excited states. The strong nuclear force, weak nuclear force, electromagnetism, and gravity were still unified or partially unified, depending on the specific grand unified theory applied. Particle interactions occurred so rapidly that no stable particles could form. The energy density was so high that space-time curvature fluctuated continuously. This environment represents the closest natural analog to the conditions recreated in CERN's Large Hadron Collider, but at vastly higher energies. NASA's quantum cosmology models describe the earliest measurable epoch as dominated by quantum foam, a term referring to the violent, unpredictable fluctuations of spacetime at the Planck scale. At distances around 10 to the power negative 35 meters, Spacetime is not smooth but instead behaves like a turbulent fluid. Virtual particles continuously appear and annihilate, and curvature oscillates between extreme values. From a quantum physicist's perspective, this foam is the natural consequence of combining the uncertainty principle with general relativity. Energy fluctuations at this scale are so intense that micro-wormholes, temporary curvature spikes, and topological defects may form spontaneously. Although these structures are transient, they influence the statistical distribution of density fluctuations that later seed galaxy formation. Since inflation progressed, the universe began to cool, though cool is relative at this stage. According to ESA's cosmology division, even a reduction of a few orders of magnitude in temperature dramatically altered the behavior of quantum fields. The inflaton field gradually lost energy, transitioning toward a lower energy vacuum state. This process, known as reheating, released enormous amounts of energy into the universe, populating it with the earliest quantum excitations. As the field stabilized, the violent fluctuations of the quantum foam diminished. This stabilization allowed the universe to transition from a purely quantum regime into one where classical physics could begin to emerge. The cooling also set the stage for symmetry breaking, where the fundamental forces separated, according to the Planck satellite's measurements of the cosmic microwave background. The tiny temperature variations we observe today originated as quantum fluctuations during inflation. These fluctuations were microscopic, smaller than subatomic particles, but inflation stretched them to cosmic scales. As a quantum physicist, this is one of the most remarkable consequences of inflation. Quantum noise became the blueprint for the universe's large-scale structure. Regions with slightly higher density attracted more matter, eventually forming galaxies and clusters. Regions with slightly lower density became cosmic voids. The statistical distribution of these fluctuations matches predictions from quantum field theory, providing strong evidence that the universe's structure is fundamentally quantum in origin. As inflation ended, the universe transitioned into a phase known as reheating, during which the inflaton field released its stored potential energy into the fabric of spacetime. According to ESA's cosmology division, this energy rapidly converted into a dense plasma of fundamental particles. From a quantum field theory perspective, quarks, electrons, and neutrinos emerged as excitations of their respective fields. The temperature remained above 10 to the power of 15 Kelvin, meaning quarks could not yet bind into stable hadrons. Neutrinos, due to their extremely weak interactions, decoupled early and began streaming freely through the universe. This period marks the first moment when matter, as defined by the Standard Model, existed in any recognizable form, although still far from forming atoms or nuclei. According to CERN's heavy-ion collision research, the early universe existed as a quark-gluon plasma, a state where quarks and gluons move freely without confinement. This plasma resembles the conditions recreated in the Large Hadron Collider, but at vastly higher densities and temperatures. In this environment, quarks constantly exchange gluons, the carriers of the strong nuclear force, creating a dynamic network of color-charge interactions. As a quantum physicist, I view this phase as a critical transition point. The strong force had not yet confined quarks into protons and neutrons. Instead, the universe behaved like a fluid of free quarks, with energy densities so high that confinement was temporarily impossible. This plasma dominated the universe for microseconds. NASA's cosmology models indicate that neutrinos decoupled from the primordial plasma, P. Although we have not yet directly detected this background, its existence is strongly supported by theoretical models and its influence on the expansion rate of the early universe. From a quantum physics standpoint, neutrino decoupling represents the first major separation of particle populations, marking the transition from a fully interacting plasma to a more differentiated particle environment. Following neutrino decoupling, the universe remained a dense, high-energy plasma composed primarily of quarks, gluons, electrons, photons, and emerging hadrons. According to ESA's early universe simulations, Particle interactions occurred at such high frequencies that no stable atomic structures could form. Photons were continuously scattered by free electrons, preventing light from traveling any significant distance. As a quantum physicist, I interpret this era as a thermodynamic equilibrium state, dominated by quantum electrodynamics and quantum chromodynamics. The plasma behaved like a nearly perfect fluid, with extremely low viscosity. This chaotic environment persisted until the universe cooled enough for quark confinement to occur, allowing the formation of stable protons and neutrons. If a strong force separated first, followed by the electroweak force splitting into electromagnetism and the weak nuclear force. From a quantum physics perspective, symmetry breaking corresponds to phase transitions in the vacuum state of quantum fields. These transitions altered the behavior of particles, changed interaction strengths, and defined the structure of the standard model. Without symmetry breaking, no complex matter could exist. Vol. Gravity was present from the earliest moments. Its influence became increasingly significant as the universe expanded and cooled. According to NASA's general relativity models, gravity is not a force in the classical sense, but a manifestation of spacetime. Curvature caused by energy and mass. In the early universe, energy density was so uniform that gravitational effects were minimal on small scales. However, as quantum fluctuations stretched during inflation, slight variations in density created regions of stronger and weaker curvature. From a quantum physicist's viewpoint, gravity acts as the large-scale architect of the cosmos, amplifying initial fluctuations and guiding matter into the structures that would eventually form galaxies, stars, and planets. According to CERN's electroweak theory, electromagnetism and the weak nuclear force were once unified under a single interaction described by the SU2 times U1 gauge symmetry. As the universe cooled below approximately 10 to the power 15 Kelvin, the Higgs field underwent a phase transition. This transition gave mass to the W and Z bosons, effectively separating the weak force from electromagnetism. The photon remained massless, allowing electromagnetic radiation to propagate freely. From a quantum physics perspective, this symmetry-breaking event fundamentally altered the behavior of particles, enabling stable electromagnetic interactions. Without this transition, atoms, chemistry, and biological systems would be impossible. Electromagnetism's emergence marks a critical step toward the universe becoming recognizable, according to CERN's quantum chromodynamics research. As the universe cooled below approximately 10 to the power 12 Kelvin, the strong nuclear force underwent a critical transition known as confinement. Prior to this point, quarks moved freely within the quark-gluon plasma. But as temperatures dropped, gluon interactions intensified, forcing quarks into stable triplets, 2 up quarks and 1 down quark, forming protons, and 2 down quarks and 1 up quark forming neutrons. This confinement is a direct consequence of the strong force's unique property. The interaction becomes stronger as quarks move apart. From a quantum physics perspective, this marks the first moment when stable composite particles existed. Without confinement, no atomic nuclei, chemistry, or complex matter could ever emerge. NASA's early universe models emphasize the critical role of the weak nuclear force during the first seconds after the Big Bang, as temperatures continued to fall. Weak interactions governed processes such as beta decay, neutrino production, and the conversion of neutrons into protons. According to CERN's electroweak theory, the weak force is mediated by the massive W and Z bosons, whose large masses make the force extremely strange. From a quantum physicist's perspective, the weak force determined the neutron-to-proton ratio, which directly influenced the abundance of hydrogen and helium produced during nucleosynthesis. Without the weak interactions, precise behavior, the chemical composition of the universe would be radically different, and stars as we know them could not form. As the universe expanded, its temperature decreased rapidly due to the stretching of spacetime. According to ESA's cosmological simulations, this cooling was not uniform. Regions with slightly higher density cooled more slowly, while less dense regions cooled faster. From a quantum physics standpoint, the expansion reduced the average energy of particle interactions, allowing previously unstable particles to decay or combine into more stable configurations. Photons remained tightly coupled to electrons through Thomson scattering, maintaining the universe's opaque, plasma-like state. This cooling phase set the stage for nucleosynthesis, the process through which the first atomic nuclei would form. The universe was transitioning from a chaotic quantum plasma into a more structured thermodynamic system, according to NASA's Big Bang nucleosynthesis models. As temperatures fell below 10 to the power 10 Kelvin, protons and neutrons began interacting through the strong nuclear force to form deuterium, the simplest atomic nucleus beyond hydrogen. However, the universe was still hot enough that most deuterium nuclei were immediately destroyed by high-energy photons. This period is known as the deuterium bottleneck. From a quantum physics perspective, the balance between formation and destruction of deuterium was governed by reaction, cross-sections, and photon energy distributions. Only when the universe cooled sufficiently did deuterium become stable, allowing rapid fusion into helium-3, helium-4, and trace amounts of lithium. This process determined the primordial chemical composition of the universe. Once the deuterium bottleneck ended, nucleosynthesis proceeded rapidly. According to ESA's measurements of primordial element abundances, approximately 75% of the universe's mass became hydrogen nuclei, while about 25% became helium-4, with trace amounts of deuterium, helium-3, and lithium-7. From a quantum physics standpoint, these abundances are a direct consequence of nuclear reaction rates, neutron decay timescales, and the expansion rate of the universe. The strong and weak nuclear forces governed the fusion pathways, while gravity and electromagnetism played secondary roles. This nucleosynthesis phase lasted only a few minutes, yet it established the elemental foundation for all future stars. No heavier elements formed because the universe expanded too quickly for sustained fusion chains. 2. Despite the formation of atomic nuclei, the universe remained opaque for hundreds of thousands of years. According to NASA's cosmic microwave background research, free electrons scattered photons continuously through Thomson scattering, preventing light from traveling freely. From a quantum physics perspective, this era is described as a photon baryon plasma, where electromagnetic interactions dominate. Photons had extremely short, mean-free paths, making the universe appear as a uniform, glowing fog. This opacity persisted until electrons could combine with nuclei to form neutral atoms. Only then would photons decouple from matter, creating the first observable light in the universe. This opaque phase is crucial because it preserved the imprint of early density fluctuations. As expansion continued, the universe cooled toward approximately 3000 Kelvin, the temperature at which electrons could finally bind to nuclei. According to ESA's Planck data, this cooling process was remarkably uniform across vast regions of space, with variations of only 1 part in 100,000. From a quantum physics standpoint, decreasing photon energy reduced the ionization rate, allowing neutral atoms to form. This transition required precise conditions. If the universe had expanded slightly faster or slower, the timing of recombination would have changed, altering the structure of the cosmic microwave background. The approach toward transparency marks the final stage of the universe's plasma era, setting the stage for photon decoupling. Recombination occurred approximately 380,000 years after the Big Bang. According to NASA's CMB analysis, this is when electrons combine with hydrogen and helium nuclei to form neutral atoms. From a quantum physics perspective, recombination represents a shift in the universe's ionization state, governed by the Saha equation, which describes the balance between free electrons and bound states. As electrons became bound, the scattering of photons decreased dramatically, allowing light to travel freely for the first time. This decoupling of photons produced the cosmic microwave background, a nearly uniform radiation field that still permeates the universe today. The CMB provides a snapshot of the universe at the moment it became transparent. The cosmic microwave background is the oldest light in the universe. According to ESA's Planck satellite, the CMB contains tiny temperature variations that reflect the density fluctuations present at recombination. From a quantum physics standpoint, these variations are the stretched remnants of quantum fluctuations from the inflationary era. The CMB's near-perfect blackbody spectrum confirms that the early universe was in thermal equilibrium. Its anisotropies reveal information about the universe's curvature, composition, and expansion rate. The CMB is one of the strongest pieces of evidence supporting the Big Bang model, inflation, and the quantum origin of cosmic structure. It is effectively a photograph of the universe's infancy, according to NASA's star formation models. The first gas clouds began collapsing under gravity. Approximately 100 million years after the Big Bang, these clouds consisted primarily of hydrogen and helium, the elements produced during nucleosynthesis. From a quantum physics standpoint, the collapse was governed by the balance between gravitational potential energy and thermal pressure. As clouds contracted, they heated up due to compression, increasing internal pressure. Only regions with sufficient mass could overcome this pressure and continue collapsing. These collapsing regions formed the first protostars. The absence of heavier elements meant cooling was inefficient, leading to the formation of extremely massive stars, far larger than most stars that exist today. The first stars, known as population 3 stars, ignited when core temperatures reached the threshold for nuclear fusion. According to NASA's stellar evolution models, these stars were hundreds of times more massive than the Sun and burned extremely hot. From a quantum physics perspective, fusion occurs when quantum tunneling allows protons to overcome their electrostatic repulsion. These early stars fused hydrogen into helium at extraordinary rates, producing intense ultraviolet radiation. Their short lifespans ended in powerful supernova, dispersing the first heavy elements into space. These elements, carbon, oxygen, nitrogen, and others, would eventually enable the formation of planets, life, and complex chemistry. The evolution of the universe, from a quantum fluctuation to a structured cosmos, is one of the most remarkable sequences in physics. Particle physics governed the formation of matter, while nuclear physics determined the universe's chemical composition. Gravity amplified density variations, leading to the formation of stars and galaxies. From a quantum physicist's perspective, the universe is a continuous chain of phase transitions, each governed by the interplay of fundamental forces. By the time the first stars formed, the universe had transitioned from a chaotic quantum plasma into a structured environment governed by stable physical laws. According to NASA's cosmology division, the fundamental constants, such as the speed of light, gravitational constant, and strengths of the fundamental forces had settled into their present values. From a quantum physics standpoint, these constants emerged from symmetry, breaking, and vacuum stabilization processes in the early universe. The first instant of cosmic history established the framework within which all subsequent evolution would occur. The universe now had rules, structure, and the potential for complexity. The chaotic birth phase had ended, giving rise to the cosmos we inhabit. Thank you for joining me on this deep exploration of the universe's first instant, viewed through the lens of quantum physics. According to NASA, CERN, and ESA, the earliest moments of the cosmos were governed by extreme energies, rapid transitions, and the emergence of the fundamental forces. Understanding this era requires the combined insights of quantum field theory, general relativity, and high-energy particle physics. If you found this journey insightful, I invite you to subscribe and continue exploring the next chapters of cosmic evolution, from the first forces to the birth of stars, galaxies, and eventually the conditions that made life possible.